laser ranging measurements correction for TOPEX Poseidon.
Okay, thank you again for the introduction. My second talk today is about the determination of SLR measurement correction function for the altimetry mission TOPEX Poseidon. To give you a little overview of the task I did, the TOPEX Poseidon mission was one of the first major altimetry missions. It was operational between 1992 and 2005, 2006. And it is a so-called reference mission for the JSON satellites and for the Sentinel satellites right now, which are in orbit. And because of that, it's of great importance as calibration or as reference for the following missions. Here you can see it's almost half of the time span of Earth observations or sea level observations we have right now. And the payload of the satellite actually was to track it, GPS receiver, DORIS receiver, and as a target for laser ranging observations, retroreflector array. And my focus is now on the characteristics of the LRA, because it was designed in the 1980s, and it's quite huge for such an instrument. It has a diameter of over 160 centimeters, and those dimensions cause phase center variations of several decimeters. And as you know, that's not suitable for an altimetry satellite, which has to detect effects of some millimeters on the surface of the Earth. We did those, those determinations because we did not have the LRA corrections, which are uniformly or previously determined by NASA, but they are not publicly available, and though we estimated our own corrections. What does that mean? To give you an explanation, what happens, the actual reference phase center is the black dot, and depending on the incidence angle of each observation into the LRA, the phase center shifts or moves along the line of sight. And I tried to find systematics in the phase center variations, and based on those found a correction function. This is a small workflow of the works we did, or I did. In the first, you have an uncorrected orbit solution, and based on these normal points which we are using for the POD, I tried to get a systematic behind the residuals, and those residuals are then used for determining the orbit, the correction function. The main information on this slide is that I have an iterative approach. I have a first iteration, a second iteration, and a third iteration. After each iteration, I get a correction parameter set. And afterwards, I finally have a final correction parameter set, which is the sum of the previous iterations. What does it mean? I will come to the details right now. But first, let me introduce two parameters, which is the first one, the SLR residual. It's the difference between the observed and the computed residual or observation. And in our initial orbit solution, we estimated range biases. Why did we do that? We had to stabilize the uncorrected orbit to converge in the right minimum. Otherwise, the entire process would not work. Though the next parameter is the combined residual, which is the combination of the actual SLR residual plus the pathwise estimated range bias. Furthermore, we did not estimate albedo effects, albedo scale factors, or empirical accelerations, because the albedo effects are acting radially. Also the range biases and also the LRA correction effect. And we did not want to absorb or any effect originating from the LRA being absorbed by the albedo range, the albedo scale factor, or any empirical acceleration. After removing some outliers from the raw data, we get the revised SLR residuals. These are then used in the main correction function. This is the basis function where I estimated the parameters, and the function which is then used to correct the raw normal point SLR observations. The input parameters are the observation azimuth and the observation incidence angle at the LRA itself, at the LRA frame, and the revised residuals. And the 6 unknown parameters are combined to a parameter set, and this parameter set is estimated for each station which tracked TOPEX Poseidon. For some stations, I chose the example Wetzel here. For some stations, we saw after the first iteration a jump in the range biases. It was not visible in the first one because the range biases were up to 70 centimeters, but after removing the most part of the range bias with the correction function after the first iteration, this phenomenon was visible. It might be that in some cases the system components at the station, for example the laser, the detector and so on, changed, and this changed the general behavior of the observations of the station. Such phenomenon were detected at 5 stations, about 5 stations of 100, though not that many. We did the detection of jumps by eye, as a colleague already told today morning, and we overcome that jump by estimating a parameter set before and after the jump to have a nice mean of almost 0 for the range biases again. Now some pictures how the residual behavior is looking like. Though in the plot A, you can see the combined residuals with the outliers. In the plot B, you can see the revised residuals, which were used for the parameter estimation. The correction function looks like this for the station Wetzel. And afterwards, you see the corrected residuals, which are close to 0. The benefits of this correction function is that the initial RMS of 33.77 centimeters is reduced to approximately 2 centimeters, which is clearly better. And we compared the improved orbit to external orbits. In this case, the GFZ SLR plus Doris solution and the GFZ SLR solution. And these comparisons show that initially in the uncorrected DGFI-TUM solution, there was a mean shift of 12 centimeters in the radial component, which is unacceptable for an altimetry mission because this error propagates to the altimetry measurements. After correcting the orbit, you get a shift or a bias of almost 0 centimeters. To be mentioned that when comparing the two GFZ solutions, they get slightly better values because they have the same background models used for the POD. And because of that, they fit better to each other. We also performed a single satellite crossover analysis. And this analysis also proves the enhanced quality of the orbit, which is enhanced with the correction function. To give you a conclusion and the outlook is that the unideally designed LRA of TOPEX Poseidon causes phase center variations, which can be enhanced with the correction function and with that we can obtain clearly better orbits of TOPEX Poseidon. The correction function and all the parameters are listed in our paper, which is recently published, And if you have any questions related to it, you can ask me, and we can talk about that in person later on or right now. And I want to thank you for your attention.
Thank you. Are there any questions?
I have seen reports by Center for Space Research, University of Texas at Austin, where they used a JGM3 gravity model and fit the orbit to 2 to 3 centimeters. So the radial accuracy was in that range. The RSS of the errors was in the neighborhood of 2 to 3 centimeters. There was an elevation-dependent correction model applied for the POD work for TOPEX during that time. Mm-hmm. Now, the errors that you are talking is in the raw data, and then you apply your model to get down to this value. So can you comment on the work done by CSR on using JGM3 to improve the orbital accuracy?
We did not use that data, if I understood you correctly. We did not use that data to correct the orbits, if I understood you correctly. We implemented the accurate attitude of the satellites. We using the offset between the real center of mass and the LRA phase center. But we did not apply any other corrections to the original observations. We took the raw normal point observations, computed a POD, and got the 33.77 centimeters RMS, arcwise RMS, out of the usage of that data.
Now, if I understand correctly, what Goddard and UT did is to correct the raw data for elevation dependence, and then use the gravitational model to improve the overall accuracy.
Mm-hmm. Yeah, maybe can talk about that later on in detail. I can also show the paper to you. Yeah.
Are there any other questions? Yes.
Thank you for the talk. I was wondering, do you apply the essentially empirical model right here, and based on the residuals? And the residuals were, so question number one is whether the station coordinates are fixed to obtain your POD, and if they are, how do you make sure that your elevation-dependent parameters are not absorbing errors in the a priori coordinates, if it makes sense?
They are fixed. The station coordinates are fixed for the determination of the correction function. And because of that, they cannot absorb any effects originating from the orbit itself.
But, yeah. The question was if the correction can absorb any mismodeling of the stations.
Yes, it can. It's not a purely as LRA correction, but a correction function for the LRA, it's the main effect, but also satellite and station-related or system-related effects, though it absorbs different sources of effects.